All right. So we're reviewing section 10.4 to begin with. The first question: 4 different types of insecticides are used on strawberry plants. The number of strawberries on each randomly selected plant is given below. Test the hypothesis that the type of insecticides makes no difference in the mean number of strawberries per plant. So it doesn't matter, just what type of fertilizer, just you use, it doesn't make a difference in the way, just the strawberries grow. That's what the test is about. So we need to, once you guys see more than 2 sets, more than 2 columns, right away it's an ANOVA test. We're testing whether the means are equal or not. And it says here, test the hypothesis that the type of insecticides makes no difference in the mean number of strawberries per plant. And I have 4 means here, mu1, mu2, mu3, and mu4. So here's how we start setting up the problem. Trying to annotate. Okay, now it's allowed me. So HO will be mu1 equals mu2 equals mu3 equals mu4. Can you guys remind me what HA is?
Not equal?
What did we say? There's a language that you have to use.
At least one of the means is different.
Yeah.
Oh.
At least one of the means is different from the others. Okay, where is the claim, guys? Is it in HO or HA? It says, test the claim that there is no difference in the mean number of strawberries.
HO.
Yeah. This is where the claim is. No difference means equal, guys. This is the type of questions, guys, I don't expect any students to do it wrong, because especially section 10.4, and that's why I did it first, because it should be very straightforward, guys. So now all we have to do now, we're going to put the data in L1, L2, L3, and L4 and run Anova test. So I'm going to give you a minute to do this with me, and while I bring the calculator up on the screen and do it at the same time. So we go to stat tests Anova, and we enter L1, comma, second L1, comma, second 2, comma, second 3, comma, second 4, and then we close. There you go. See, it's as simple as that. And then we press enter, and we get the test statistic, and we get the p-value. So let me just write down what we did. So Anova, L1, comma, L2, comma, L3, comma, L4. F equals, when the test statistic is large, guys, the p-value will be small, 8.36, and the p-value equals. Okay, we need to move the decimal place 4 digits to the left. So that would be, guys, E minus 4, that would be 0.008, which is definitely very small, less than alpha. And I don't need the calculator now. I can let the calculator disappear. So p-value is 0.008, which is less than alpha. Reject HO. And what is the conclusion? There is enough evidence at the 1% level of significance to reject the claim that the means are equal, or to reject the claim that the type of insecticides makes no difference in the mean number of strawberries. So there is enough evidence to reject the claim. And you ask me why you didn't say use the word support, because the claim is in HO, and I reject HO, so then I reject the claim. Just the same technique, the same guidelines as we used in chapter 7 and 8, guys, we will be using here. Any questions about this question? This question covers whatever you need to know, just everything that you need to know in section 10.4. This is 10.4. So in 10.4, guys, when you set up the hypothesis, you're going to put HO mu1 equals mu2 equal whatever, how many means. If it gives you 5 sets, you go to 5. And then you're going to put HA, at least one of the means is different from the others. Then you're going to run ANOVA. You're going to get F, you're going to get p-value. If the p-value is less than alpha, you're going to reject HO. And if the p-value is more than alpha, you're going to fail to reject HO and then write your conclusion. Any questions about this question right here? Okay, let's go to the next one then. Let me clear here. Number 2. When you see a table, guys, that has headings in the rows and headings in the columns, it's an independence test. That's section 10.2. And he will be asking you whether, just the variables are dependent or independent. So if the question is about variables are dependent or independent, it is an independence test, which is section 10.2. So a sports statistician is interested in determining if there is a relationship between the number of home team and visiting team losses and different sports. So they want to check if there is if there is a difference between, if there is a relationship between the type of sport and whether, just the team is a home team or a visiting team when they lose a game, if there is a connection between the two. So we want to see if there is a relationship here. A random sample of 526 games is selected and the results are given below. Use the p-value method to test the claim that the number of home team and visiting team losses is independent of the sports. So this is the independence test, guys. And as I told you on Monday, when you state the null in the alternative hypothesis, you state him this way. HO will be the variables are independent. But here he tells me what the variable are. So the first one is the sports itself, the type of sport, and the second one, whether it is a home team or a visiting team. So HO will be number of home team and visiting team losses is independent of the sports. Number of home team and visiting team. I'm going to turn my document camera on because I'm not happy with the way the annotation is going. So number of home team and visiting team losses and sports are independent. No, I'm not right there, so let me just skip the.
You said this was 10.2?
Yes,
Thank you.
that is 10.2. So the null hypothesis is number of home and visiting team losses and sports are independent. And HA will be number of home team and visiting team losses and sports are dependent. This is a chi-square test. As I showed you on the calculator, we put the data into a matrix, and now we're gonna run a chi-square test. So I'm gonna bring the calculator back up on the screen. Okay, can you see the calculator, guys?
Yes.
Okay, good. So let me show you how to perform the test now. So you go to stat, tests. I would scroll up because these are at the bottom. Come on. Here you go. Guys, the next one, D, is not it's a chi-square, but goodness of fit test. This is for section 10.1. And letter C, guys, is for section 10.2. So let me just say that. So chi-square test is section 10.2. Chi-square goodness of fit test is section 10.1. And Anova is section 10.4. What you will get from me, guys, for the final exam, a list of all those features and where to use each one. It's going to be like a 2-page list of shortcuts using the calculator. So that should help you a lot. For HO and HA, HO will be always the variables are independent, and HA will be the variables are dependent. As you notice in the table, the heading of the table were sports on one heading and visiting and home teams. So we say visiting and home team losses and sports are independent, and then the alternative will be always that the variables are dependent. Okay. The observed values are what's given to you in the table, guys. The expected value, the calculator is going to find them for you, so you don't need to find them. And all we need just to hit calculate. There you go, guys. I got the test statistic and I got the p-value. So chi-square is 3.24. Usually it's 3 decimal places. So 3.290, sorry. And p-value, as you can see, it's a big p-value here, is 0.3490, which is bigger than alpha. We failed to reject HO. And I forgot to mention where the claim is. So let me just bring back the question and you guys tell me where the claim is, because the last statement is based on where we have the claim. Yes, always. Some students are asking me to clarify HO and HA. In section 10.2, yes. Variables are independent always in HO. Variables are dependent always in HA. So that does not change at all. And let me see. Okay. Test the claim that the number of home team and visiting team losses is independent. Once you see the word independent, guys, you know that the claim is in HO. When he says related or dependent, then the claim is in HA. So just keep that in mind, please, when you do that. So I'll close this and I'll bring back the screen. We don't need this now. All right. So my claim, guys, happen to be here. Fail to reject HO. There is not enough evidence at the 5% level of significance to reject the claim that I'm just going to copy and paste HO, that the number of visiting team losses and home team losses are and sports are independent. We say we don't reject the claim that they are independent, so probably they are independent because we're not rejecting that. All right, so this is one question from section 10.2, guys. Any questions? As you notice, the same 5 steps: stating the null and the alternative hypothesis, finding the test statistic, finding the p-value, decide to reject or fail to reject the null hypothesis, and then finally write your conclusion whether you support or fail to support the claim, or reject or fail to reject the claim. It's exactly the same thing as we did in chapter 7 before. Okay. Now what I'm going to do, guys, I'm going to do an example from section 10.1, just to review section 10.1. Okay. Number 8. It's on page 532. A researcher claims that the number of cups of coffee US adults drink per day are distributed as shown in the figure. So they think, this is what he believes, that 26% of Americans drink 1 cup. 36% of Americans drink no coffee. 19% drink 2 cups. 8% drink 3 cups of coffee, and 11% drink 4 or more cups. That's what they believe. We want to check whether this belief still holds or not. So you survey people. You randomly select 1,600 US adults and ask them how many cups of coffee they drink per day. The table here shows the results. Those values, guys, are called the observed values. The observed values that you get from your survey. When you survey people, they answer your question. These are called the observed values. Test the researcher's claim. Okay, so the first thing that we're gonna do, guys, before we do anything else, we're gonna put this data right here in L1. These are observed values. So let's do the observed values in L1. Let me do that together. And then we can write, just the solution of the problem. So I'm going to go to stat, edit, and then we're going to go to L1. And then I'm going to scroll up and then clear. And okay, let's enter the values, guys. So it's 570. I'm going very slow, guys, because I want you to just follow up with me. 432, 282, 152, and 164. Now for this test, this is a goodness of fit test. When he give you a distribution of more than 2%, this is section 10.1. It's a goodness of fit test. You need expected values. Can a student remind me how to find now the expected values? What do we do to find the expected values? You have to put them in L2. The calculator wants to know the expected values as well. That's what we started on last Wednesday. So how do you find the expected values, guys? Can someone remind me?
From the percentages,
Yes.
don't we have to multiply them by 100?
You take the percentage, you don't multiply by 100, you multiply by the total.
Oh,
What's
I'm
the
sorry.
total
Okay.
here? Which is what? 1600. So guys, for the expected values, you take the 36%, what did he start with? 0. You take the 36% and multiply by 1600. Then you take the 26% and multiply by 1600. Then you take the 19% and multiply by 1600. Then the 80% multiply by 1600. Then the 11% multiply by 600. And then you get your expected values. Once you have in L1 and L2 the observed values and the expected values, then you can run the test. Okay? So let me write the percentages and just move the book away. So we have for 0, you have 36%, then 26, then 19, then 8, then 11. And if you add up the percentages, guys, they should add up to 100%. Let me see what we have in the chat. Oh, is my voice breaking up, Mandy? Is it clear now? Oh no, yeah. What about now? Yeah, I noticed that the voice was breaking up. What about now? Okay, good. Thank you. I'm glad you said something. Lucia, you have a question for me? Go ahead if you have a question. Okay, great. Thank you. So I'm sorry about the voice thing. I don't know why this happens, although I have two microphones, just sitting next to me. So we put the observed values in L1, and I was talking about the expected values. Let me repeat what I said about the expected values. You're definitely going to see a question like this on the next test, guys, next week, and on the final exam. So be prepared. Whatever I do with this question, you're going to do, just on whatever question you get. You take each percent and you start with 0 because the observed value starts with 0 cups 570. So for the expected values, you do 36% times 1600, 0.36 times 1600, 0.26 times 1600, and so on and so forth until you get all the expected values. And let me demonstrate, guys, how to do this problem. I already have the data, so I don't need the book. We're just gonna do the question and show you how to do this. So number 8. Page 532. HO will be distribution of coffee cups is as claimed. HA, can someone remind me what's the HA? It's always a generic language. You don't change, guys. So HO will be the distribution as given to you as expected. What would it be, HA? Distribution, what? Is not as claimed, or distribution, you know, just of coffee drinkers, or here coffee drinkers, has changed or is not as claimed. If you're using my math lab, if it has an option to say has changed, you select that one because it is the same as is not as claimed. And since the researcher claimed that distribution is the following, and we want to check the researcher claim, so the claim happened to be in HO here. We're going to run a goodness of fit test. It's called GOF chi-square test. You're going to put the observed values in L1. And then the expected values in L2. And what are the expected values, guys? We're going to begin with 36% of 1600. Then you're going to do 0.26 times 1600. Then you're going to do 0.19 times 1600. Then you're going to do 0.08, 8% of 1600, and then 11% of 1600. You can do the math here, or you can do it on the calculator. So let me show you. I can do the whole thing on the calculator. I don't have to do it right here. So for L2, you just put 0.36 times 1600. And it will do the math for you. Oh, they're very close. 0.26 times 1600. Again, that's a close. 0.19 times 1600. 0.08 times 1600. And then finally, 0.11 times 1600. If you add those up, you're going to get 1600. And if you add those up as well, you're going to get 1600. What do you guys think? Do you think the distribution has changed? These are the observed values, the values from the research, and these are what we should have expected. Do you think that there's a lot of difference between the two? Any thoughts? If there is not much difference, you're going to fail to reject HO. If there is too much difference, then you're going to reject HO. I don't see a difference between these two right here. Not much between these two. So probably the distribution did not change much. So we'll see. Let's run the test and decide. Okay, so you go to stat. Let me show you this right here. And then you go to tests. There you go. Then you go to goodness of fit test. Okay, right here. If you have a TI 83, the goodness of fit test is not there. That's why probably you have to download the emulator. And then look, observed is L1, expected is L2, And the degrees of freedom, guys, is number of categories minus 1. Let's see how many categories. We have 0 cups, 1 category, 1 cup, 2 cups, 3 cups, and 4 or more. So I have 5 categories. 5 minus 1 will be 4. So it is a 4, correct. And then hit calculate. And here's the test statistic, and here's the p-value. So chi-square is 7.588. And p-value is, as you can see, guys, 0.10788, which is bigger than alpha. I think alpha was 5%, so that's bigger than alpha. Fail to reject HO. There is not enough evidence at the 5% level of significance to reject the researcher claim. You ask me why I use the word reject, because the claim is in HO, to reject the researchers. And you notice, guys, there wasn't much difference between the observed values and the expected values. If you don't see much difference, so likely you're going to fail to reject HO. So that concludes this question from section 10.1. We're going to get a more chance to do some more problems when we do the review for the test. So you will see some more. But I think this question, guys, is very comprehensive. It should cover everything that you need to know in this section, which is section 10.1 here. Any questions before I